Hello friends, in this session we will study the more characterization of continuous function. Our first characterization is nothing but the fundamental definition of continuity. So what is that characterization? So to see the theorem, let xd and y row be metric spaces. Xd and y row be metric spaces. Then function f from x to y is continuous if and only if f infer g is open in x. G is open in x whenever g is open in y. G is open in y. Why this is known as fundamental definition of continuity? Because in topological space, definition of continuity is nothing but this one. If I have two topological spaces, x tau 1 and y tau 2 are two topological spaces, then function from f from x to y is said to be continuous if inverse image of every open set is open. And our epsilon delta definition, sequential continuity concept, that doesn't hold in topological spaces. And that's why this is the fundamental definition of continuity. So, but here, as you are well familiar with definition of continuity with epsilon delta in calculus, and so firstly we have taken that concept and we are generalizing it now for metric spaces. Okay, so proof. So let f from xd to y row be continuous function. Xd to y row be continuous function. What is your claim? F inverse g is open in x whenever g is open in y, and GB open subset. GB open subset of y. Your claim is F inverse g is open in x. So for this we have to show that for every point in F inverse g, there exists open sphere which is completely lies inside in F inverse g. Okay. So let x belongs to F inverse g. This implies then fx belongs to g. Fx belongs to g. Now since g is open in y, therefore for fx belongs to g, there exists some epsilon greater than 0 such that open sphere S epsilon f of x is completely lies inside in G. Now, since f is continuous function, therefore f is continuous at x belongs to G, and therefore S epsilon fx contains f inverse of this contains S delta x for some delta greater than 0. For some delta greater than 0. Okay. Inverse image of every open sphere about fx contains some delta open sphere about X. Is it clear? Means this S delta X must lies in F inverse G. Okay. So this is 1, this is 2. From 1 and 2, F inverse of, S delta X is contained in F inverse G. If I take inverse image on both sides, F inverse of this must be subset of F inverse G. Okay. Thus, for every x belongs to, F inverse G, there exists delta greater than 0 such that S delta X is contained in F inverse G. And therefore, F inverse G is open. Is open in X. Now we'll prove converse part of this. Conversely, suppose F inverse G is open for any open subset G of X. For any open subset open in X, for any open subset G of Y. What is your aim? Claim F is continuous function. F is continuous function. Okay. So let X belongs to X. Then to show for given epsilon greater than 0, then to show F is continuous at X. That is, for every epsilon greater than 0, F inverse of S epsilon Fx contain S delta X for some delta greater than 0. Is it clear? Now, for epsilon greater than 0, yes, epsilon Fx is open sphere in Y and hence open set in Y, and therefore F inverse of S epsilon Fx is open in X, and therefore for X belongs to F inverse of S epsilon Fx, there exists some delta greater than 0 such that S delta X is contained in F inverse of S epsilon Fx, and therefore F is continuous at X belongs to X, where X is arbitrary. And therefore F is continuous at every X. F is continuous at each X belongs to X. And therefore F from X to Y is continuous function. Now we know that a subset F of metric space is closed if and only if its complement is open. So due to that, and this necessary and sufficient condition for continuous function, we must have necessary and sufficient condition in terms of closed subsets also. So let XD and Y be metric spaces, then function F from X to Y is continuous if and only f inverse f is closed in f inverse f is closed in X whenever f is closed in Y. F is closed in Y. Okay. So suppose f from xd to y rho be continuous function and f be closed subset. F be closed subset. Claim f inverse f is closed. For this, it is sufficient to show that f inverse f complement is open in X. That is to show f inverse f complement, which is X minus f inverse f, f inverse f is closed in X, is open in X. Now since f is closed in Y, therefore f complement is equal to y minus f is open in Y. Now f inverse of f union f complement is equal to f inverse f union f inverse, sorry, here we'll take f inverse f union f inverse f complement. This is same as f inverse f union f complement, which is equal to f inverse y, which is equal to x, and f inverse f intersection f inverse f complement. We know that inverse image of union of two sets is union of their inverse images, and inverse image of intersection of two sets is same as intersection of their inverse images. So f inverse of f intersection f complement, which is equal to f inverse phi, which is equal to phi. This implies f inverse f and f inverse f complement are complements of each other. Complements of each other in X. Okay. Now f complement is open. Now f complement is open in X and f is continuous function. F is continuous function implies f inverse f complement is open in, here y, f inverse f comp is open in X, and f inverse f, and these are complements of each other. Therefore from 1 and 2, what will get? F inverse f is closed in X for any closed subset, for any closed f in Y. Is it clear? Conversely, suppose Conversely, suppose f from xd to y row be function such that f inverse f is closed in x if and only if f is closed in y. Closed in y. Right? Claim f inverse f is closed in x if f is closed in y. Claim f is continuous function. For this, it is sufficient to show that f inverse G is open. Okay. For any open subset G of x, y. Okay. That is to show by sufficient condition. It is sufficient to show. It is sufficient to show f inverse G is open in x whenever G is open in y. Open in y. So let G be open in y. Then G complement is closed in y. Moreover, G union G complement is equal to y and G intersection G complement is equal to phi. Implies f inverse of G union G complement is equal to f inverse G union f inverse G complement is equal to f inverse y is equal to x and f inverse G intersection f inverse G complement is equal to f inverse of G intersection G complement is f inverse phi. This must be equal to phi. Implies f inverse G and f inverse G complement are complements of each other. Complements of each other in X, where f inverse G complement is closed in X by hypothesis. Implies f inverse G is open in X. Okay, for any open set G in Y, and therefore f is continuous function. F is continuous function. So thus here we have proved two necessary and sufficient conditions for continuous functions. We'll take more